Okay, good afternoon, everyone, and welcome to another Talk Tuesday with Dr. Shashi Shakhar. Dr. Shakhar is the McKnight Distinguished University Professor and a University Distinguished Teaching Professor at the University of Minnesota. And I attached the illustrious bio in our calendar as well, but I will mention he has over 350 publications in the spatio-temporal space, and also has written a popular textbook on spatial databases and an encyclopedia of GIS. And hundreds of his mentees are all over the country and probably even the world, leading many such efforts. So with that, I'll hand it over to Shashi for the talk. Thank you for being here.
Great. Thank you, Vandana, for a very nice, warm introduction. So first, I just wanted to check on my screen. I see the PowerPoint slideshow, and I also see a little screen with a couple of faces from the meeting. So I just wanted to confirm, on your screen, are you only seeing the slideshow or are you seeing something more?
Just the slideshow.
Okay, great. All right. So today, so I want to share a little bit about spatial data, particularly spatial data mining. And you can kind of see the color of my glasses. I came to this field at the beginning of my career, and I have learned mostly through projects. So this iHARP is another exciting opportunity because we haven't worked with polar data before, which brings a lot of new challenges. But I generally wanted to share what we have learned. I mean, this data mining, particularly for spatial data, a lot of progress has been made in this century, and that's what I will share. But before that, let me also share my excitement about the spatial world, because between last century and this century, it has actually changed dramatically. If you go to last century, which is first column, then you had maybe a few million users of ArcGIS, and there were a few other niche software that were around. But as you come to this century, billions of people are using, right? You see navigation services like Google Maps, Apple Maps, E911, and so on. And, last 10, 15 years, you will also see ride sharing. And now during pandemic, food delivery and all kinds of things, this really became essential services for our lives. So certainly in consumer world, I mean, this has become as essential as electricity and water. And also even from scientific side, some new things are happening. So a lot of spatial data has become now available on the cloud. It's easy to access, and many of the colleagues in this project are using it. And they have been used widely in agriculture, transportation, and other areas. Right? So this is just to repeat that message. Even GPS receivers, probably many of us know it's not only for location, but also most of the clocks, whether it's internet or telecommunication, I mean, they are all synchronized through GPS. So it has become a very essential part of our lives. And people are so worried about its failure that they're developing ground-based systems, right? So this is becoming a very ubiquitous thing. The second big, I would say, impact in this world is coming from the remote sensing data. And a lot of that is used in polar sciences. But many other areas also, these are being used, right? And there are lots of satellites today scanning the Earth daily at a pretty high resolution. So many new applications are coming up. Now, these data sets used to be very big. At the beginning of my career, we needed specialized ways to download it, but that also has gotten easier. So Google Earth Engine, I know some of the colleagues are using it here. It has many of the satellite data sets. And now AWS Earth has some, NASA also had some of these. And some of these data sets actually come with labels. So the DARPA's geospatial cloud analytics, they started using machine learning very heavily. And geo-AI usually is the term used to run things like CNN, to analyze satellite imagery to get buildings, roads, and all kinds of other surface features. Right? So there's again, the data set is available and the access is getting better, right? And that's sort of very similar to many of the arguments made in iHARP. Okay, so with this, let me actually take you to kind of an old story about why spatial data mining may be of interest to scientists. And given the pandemic, I think this story, even though it's fairly old, it is still relevant, right? So, so this is 1854, and many of us have probably seen this map. Okay, back then cities were new and they used to suffer from many infectious diseases, and not all of them were very well understood. So, for example, cholera, the prevalent theory back then was Maizama or bad air theory, saying that it is spread through air, bad air. Um, and John Snow in this epidemic actually, made a map where you see little dots are the deaths, and these bigger squares are pump. And in this map, he saw a very interesting pattern that these deaths were localized in London, in one area. They were not all over London. And second, the center of this was a Broad Street water pump. So he felt there was some connection. And in fact, he did a little bit more work. There is a small bar here, which is a little hard to see, but patrons of the bar actually did not get sick because they were primarily consuming beer and not the water from Broad Street. So in some sense, there was a natural experiment, and he was able to make arguments to push the fledgling germ theory, saying there is something in the water. Since the science was not with him, it took a couple of days, but one of the city official finally said, let's do an experiment, let's take off the handle. And it did subside the disease. And pretty soon, Louis Pasteur and others, they started pointing microscope at the water, and they did control experiments and so on. So this conjecture, which is, or the pattern that was observed by John Snow, gave a new hypothesis for science, right, which actually bolstered the fledgling germ theory, which is now considered a turning point in science. It has changed, hygiene, modern cities and so on. But this story tells us about the strength and weaknesses of spatial data mining, right? It can help us find these patterns, which can help generate hypotheses, which could be further tested through natural experiments around spatial variability. But one has to still follow up with the rest of the science, whether it's controlled experiment or theory development and other things to take it further, right? But it's a thing. It's a very nice win-win. The science got some new methodology, and it was also helpful for, you can say, spatial data science itself. And I will show new tools were developed to find patterns like this. And today, this is broadly under this big data or fourth paradigm. And I hope in iHARP we find some similar opportunities to get a win-win where the spatial data mining finds some interesting patterns to generate hypotheses. And also we try to see if our tools scale up to the new challenges of polar data, right? So that's the hope. But with this, now we can switch and talk about, the language of this world of data mining, words we use and what they mean. So broadly, data mining is a field that arose in 1990s, so a little about 30 years ago. First workshop was 1993. And people were very excited by the growth of the data. And a number of people from business and government were saying the volume of data is growing so fast that it's not possible for the human analyst to analyze it. Probably it's the case in polar science as well. And we'll love to hear that from our colleagues. And there were different tools they were being developed to analyze data. The older tool was a relational database, SQL3, where you could go and analyze very big data. Back then, the statistical tools like SAS, they could not actually scale up to data sets which could not fit in main memory. And back then, the main memories were very small. So this data mining field was kind of born to try to, in some sense, find a compromise between statistics and computational scalability. And but not only that, they also defined new pattern families. And around turn of the century, there was a workshop to bring data mining and GIS people together, 1999 in Seattle. I was there, and we actually walked out of that workshop feeling that there was a big mismatch and new things had to be done, right? So a lot of us started working on reducing that mismatch, right? And this field of spatial data mining started. And what we did was to take the basic definition of data mining, which is centered around patterns. This is a core notion, and I will show you some examples pretty soon. And they use 3 adjectives here. The patterns have to be useful. So this is a use-inspired field. This is not a fundamental theory building field, right? So we want to work with specific domains, as we say them, and make sure that what we are doing is useful to them. And what we try to do is to find patterns of interest to the end users. And also the word non-trivial is here because the search space is very large. If there are only a couple of patterns and people can just use their current tools, then it's not of interest to data mining, right? But this is a large search space. You need algorithms and computers to help. Only then it becomes part of data mining, right? And only thing we are adding here is for spatial data mining, we are saying the data sets are spatial. Certainly in case of polar science, we believe a lot of data is spatial. Okay. So let's go and look at these patterns. What do they mean? Now, classical data mining had its own pattern families, and occasionally I will go refer to them. And as I mentioned, we felt that they were not adequate. Um, so 4 pattern families where people have started in spatial world are these 4, and I will illustrate all. But there are other ones which we can add. I believe change detection would be a key pattern family of interest in iHARP, and it will be really great to work together and try to formalize it so that it is useful to polar science and at least also has some computational challenges there. So let's go look at what these patterns look like, and I just want to illustrate them so we get an intuition. So the London cholera story, is linked to the first family of patterns called hotspots. And this probably all of us have heard this a lot during pandemic, so I'm not going to dwell on it too much. Intuitively, it's a geographic area where the density of some phenomena is much higher inside that area than outside. Okay. John Snow's case, it was done more intuitively, but recently there are tools. For example, National Cancer Institute, which does this kind of analysis all the time, they have a tool called SaTScan, which can find circular footprints where the inside density is much higher than outside. And they have some statistical, further post-testing. So if you ran their tool on John Snow's map, it will give you this circle, and it will say that the inside density is much higher than outside in terms of log likelihood ratio. It also checks whether such a high density can happen by chance if you throw darts and in this space. And what it is basically showing you is that probability of such a dense cluster happening by chance is very small, less than 1 in 1,000 or so. Okay. So this is one family, very simple, and we'll revisit this in more detail. Let's look at another family, which is the flip of hotspots, and we call them spatial outliers. And you can think of them as discontinuities, spatial anomalies, and so on. And I will show you one example from our own work. So this is from the traffic data from Minneapolis-St. Paul area. There are about 4,000 sensors on the highway. And we were analyzing some of this, and we found an interesting discontinuities on this Interstate 35W, which has about 60 stations, each with about 4 sensors. But if you look at this, the station number 9, okay, look at station number 9, it's traffic measurement, which is this color coded. Dark blue means low and red means high. But you notice station 9, it's reading individually, they are not outliers because there is plenty of teal color in this plot. But they're still unusual because they're very different from their upstream and downstream neighbors. And this is thought of as a spatial discontinuity or an example of spatial outlier. So when our algorithms detected that, we took it to Department of Transportation, and they went checked the sensor. Turned out it was a bad sensor, and they replaced it. But there are many other applications like that. Right now, we have another project with Department of Defense looking at ship trajectories and their gaps, and finding outliers of this kind, which trajectories look very different than other trajectories in the neighborhood and so on. Let's go to other pattern families. Here is prediction. And of course, in physics and so on, you have much more sophisticated prediction tools. But these are simpler prediction that have been dealt with in spatial world. So for example, here these red crosses are bird nests. And this came out of a thesis in ecology in University of Minnesota, where the person went and surveyed this wetland and divided it into grid. And there are about 5,000 cells, and he measured things. So he marked down where the nests actually occurred. This green area means there was vegetation. And he had several variables which are condensed into these other maps. So this left bottom map is showing vegetation durability. So when wind comes, will it sway or not? Because that can affect nest location. Distance to open water, because again, predators can come in. So there are several variables. But the problem is, given all these maps, we want to predict locations of nests. So it is kind of like a prediction problem, but all the variables are maps. And later on, we will see why that prompts us to use slightly different models than classical statistics or machine learning. Let's go to one more pattern family, and this is called co-location. For full disclosure, I should mention this was advocated or created by our group, and some of the earlier publication on collocation pattern came from my group. But the intuitive notion has been around for a very long time. So for example, I'm showing you Second World War shipbuilding and cancer incidents in US around 1950s and 60s. Back then, lung cancer was a much very prevalent. Uh, you know, with lot of other interventions, this has gone down, not as important, relative to many other cancers today, but back then it was one of the major ones. And you see a curious co-location. You see these red areas which have high rate of lung cancer in 50s and 60s. And you notice also that, we are showing you shipbuilding activities in Second World War, and you notice they seem to be co-located. Okay. Later on, it was traced to the use of asbestos in shipbuilding and so on. And so on. So this is sort of intuitive notion of co-location. So the notion has been around, and we'll talk about how it is quantified and so on. In fact, to give us a feeling for this pattern, let me actually pause here for 10-15 seconds. So here is a cartoon map with many features like green tree and house and blue bird and fire and dry tree. So let me ask you the following. Do you see a pair of things which are co-located? Whenever you see one of them, you see the other one nearby. And I will pause here for about 10 seconds, and you can just open up microphone and say it. That will be easier than me trying to monitor the chat. So this map, do you see a co-location? And this is the combinatorial view, where there are many features and we are looking for things which often happen together in space.
I see bird and house together.
Okay, bluebird and house, that's one pair, and you see them often together. Not always, sometimes they are far apart. Any other that we see? Okay. Tree and fire, okay, Jianwu is saying, and great. So, but this is illustrating the combinatorial aspect of it, because if you have many features, then one has to think about, there could be many pairs and many triples, and that's when it becomes more interesting data mining. If you had a single pair, then those tests are known, and I will show you some of those tests. But it's the combinatorial aspect which brings it to the domain of data mining. Okay? All right. Also, in terms of scope, as I said, in this discussion, we are not interested in simple things that can be done in SQL, or if the search space is very small, if you just have one or two pairs, and so on. And also, we want it to be interesting because some things are very well known, nearby things are related, which the data mining can reveal, but that's not what you're interested in, and so on. Okay. All right. So let me pause here for a quick minute, see if there are any questions on the motivation part on this. All right, so I'll proceed with the next part. I very quickly wanted to say a little bit about spatial data, and some of us have been using these tools, but if you're new to these tools, then I did want to share one development that's worth being aware of. Okay. So spatial data comes in many flavor, right? So first, what is a spatial data? And it's as simple as if a data has a location, whether it's on the surface of the earth or somewhere else, then we think of it as a spatial data. And it comes in three flavors. Raster data are like satellite imagery. Vector data is when we have actually extracted geometric features and represent them as points, lines, polygons. And if you are working in a flow network, whether it's water flow or traffic flow, then we often model it as a graph. So these are sort of three flavors. Out of these, at least the second one has been, matured quite a bit in recent years. So this, I'm showing you a standard, Open Geospatial Consortium, and it actually provided 6 data types: zero-dimensional point, line string, polygon, and their collections. And these have been implemented as a library in many software. It also has a set of functions, simple things like distance, but you also have buffer in the sense of geographic buffer, some topological operations and so on. And this has been implemented, as I mentioned, in many software. And not only the library is implemented, there is also data structures like R-tree. Because if you're just used to the basic SQL, it actually works well for one-dimensional data like number or text string. Doesn't work very well for two-dimensional data like point in a two-dimensional space, because they often use sorting and B trees, which are not very effective in multidimensional space. So these software have actually two-dimensional data structures like R-tree and so on, and they are widely available. Even in cloud platform, there are similar issues. If you just use generic Hadoop and so on, they often partition the data using techniques like random, which are not very effective for spatial data. So there are extensions of cloud. For example, you see ESRI tools for Hadoop or spatial Hadoop and Cyber GIS and so on. They have actually brought these kinds of two-dimensional data structures and partitioning methods to cloud. But these tools have matured, and it's good to be aware of them. And hopefully some of us are using it. Okay? And they are widely available. Of course, these tools themselves are evolving. For example, if you want to model the ice sheet, which may be a three-dimensional structure and so on, the current tools don't support them very well. And this is an evolving area, and more things are coming. So that was the primary thing I wanted to share about the data. But right now, a lot of the discussion that will follow would stick to simpler data like points and so on. Right? So this was one other basic thing. And I'll next cover a little bit about statistical foundation. But before I go there, any quick questions on the data types that we will focus on? Okay. All right, so very simple so far, and it will stay pretty simple next section as well. So let's go and now look at it from a statistical perspective. And so one of the things that many of us probably know is traditional statistics often made assumptions which do not work well for spatial data. And I will show you a couple of such assumptions. So one such assumption is this i.i.d assumption. If you're using linear regression or classical neural networks or many techniques in machine learning, they often make this assumption. Data samples are drawn independently of each other from identical distribution. For spatial data, this is troublesome, and I'll show you, details and try to persuade you that we should move away to more powerful methods. And slowly, some of those are coming to machine learning as well. So when you go to CNN, it captures autocorrelation. But some of the other issues like the heterogeneity, less well modeled, so on. Right? So this is sort of one dimension of weakness. The other dimension of weakness is something geographers know very well, but in the general machine learning data mining statistics literature, it's not talked about as much, even though it's a very old idea. But let me illustrate that here. So suppose I'm looking at this spatial data, which has three types of events, red, blue, and yellow. And I want to ask which colors are co-located, kind of the question that I was showing you earlier. Now, if you go with classical statistics, it would bring up techniques like Pearson correlation coefficient. And what I'm going to show you here is that may be inadequate for this problem. Because in order to use Pearson correlation coefficient or regression, you need to divide the space, discretize it into vectors, right? This is based on vector algebra. And you need to cut up this continuous space into a set of vectors. So if you cut it up like this, then there are, four vectors. This vector red and blue is 1, but yellow is 0, right? Here, yellow is 1, but blue and red are 0. So if you look at these vectors, you can easily, compute this, and you will see that it will say that red and blue have high correlation, but yellow has low correlation with the other colors, right? But notice that this result will change if the partition was changed, right? So if I move this vertical line a little bit to the other side, suddenly your Pearson correlation coefficient is telling you a completely different story, okay? In other words, such measures are unstable. If you force your continuous space to be partitioned, which is very commonly done by classical machine learning and data mining and other people, then your measures, their results are sensitive to the choice of partitioning. By the way, in real life, if you have ever heard of gerrymandering, how election results can be, biased towards a certain group, it's the same kind of a problem that can happen here. Of course, we can't claim that there is a political, reason or a, some other social aspect here, but you should be aware of that lot of classical techniques. If you have to partition continuous space, their results become dependent on the way you partition it. And it's very hard to actually disclose and quantify because there are so many ways to partition it, okay? So in spatial statistics, we get away from this partitioning business, and they instead draw a neighbor graph. So for example, here, suppose based on distance, you connect the nearby things, okay? Of course, you can say, well, whatever you compute will be function of distance, but that's much easier to handle, and I will show you how we handle it, right? So we first basically create a graph, which you can think of it as a neighbor graph. You can represent it as a matrix if you like. And then there are statistics which are defined on that graph. And now these statistics are, since they are not using partitioning, you don't have to worry about partitioning. But they are function of distance, which is used to define the neighbor. And that is explicitly modeled, okay? So this is another big departure. And we'll come back to this when we talk about collocation again, okay? So spatial statistics, many of you know, is a field, again, has developed for decades and decades, almost goes back 100 years or more. It had many nice, clean mathematical theories, but its adoption was slow because these techniques are more data hungry and they also need more computation. And both of those have come around, the turn of century. Now the computers are powerful enough and we have a lot more data. So these techniques have become much easier to use. And that's in some sense what we are arguing in this talk. And then these techniques can be brought in to improve some of the data mining and machine learning methods, which are, the generic methods. So let me actually illustrate this a little bit. So let's start with one basic notion, spatial autocorrelation, which, I said in geography, there is a simple description, a descriptive thing, which says nearby things are similar. But in spatial statistics, we have functions like k function Moranci. So if you don't agree with that, you can actually compute these functions and their value will actually tell you where the independence assumption is valid or not. Okay. And I can also convey this graphically, but everyone from polar science, you are in physical space, so I don't think I have to convince you about it. But this is a map where pixel properties are drawn independent of each other. And you kind of see this looks like white noise, whereas the real maps, you have very smooth variation and nearby things are similar. So if your maps look like this, then probably i.i.d assumption is not helpful. And if you still fit those models, your results will be weaker than they can be. And your errors would also show spatial patterns. But here are some functions. If you're just dealing with points like these, points in a space, then there is a function called Ripley's K function. And what it basically does is the following. It basically, for each point, it takes a point and draws a circle around it and counts how many more points are in there, right? So if these points were independent of each other, then you can imagine that, in an area, in a circle of radius h, the number of points will be proportional to area of the circle, right? And that's this solid line. And it is expected if the points are independent of each other, then the k function value would be proportional to the pi h square, okay? And this is sort of complete spatial random, and that's where you will get that. But the real data, if it is clustered, you're going to get a much higher value, okay? Or if it is declustered, you will get a lower value, right? So this is one function. And such function, you can also use it for cross correlation kind of things. The main difference here is if you are putting circle around, say, house, then you will count birds and vice versa, okay? And I'll just show you in our data set when we were looking at this. Remember, we said that fire and dry tree seem to be co-located, house and bluebird seem to be co-located, and their Ripley's cross KC is much higher than this, the independence assumption. Okay, but some of the other pairs, they are flop-flopping around the independence assumption. By the way, this is the mean, and with Monte Carlo simulation, you can get a standard deviation band and get statistical significance. Okay, so this is sort of one type of function that is used. So autocorrelation is a one big thing, and I'll revisit it, but the spatial variability and heterogeneity is also another important thing. And we all know that if you don't pay attention to that, let's say if your data is like this, X and Y axis, if you fit a global model, it may say positive relationship, but this data clearly is not homogeneous. So if you separate it into homogeneous population and fit your models, they may tell a completely different story, right? In Geography, again, things are, people believe things are different. Some part of physics may be universal, but we all, for example, what you see in Greenland and what you see in Antarctica, there are some differences, right? So fitting a purely data-driven model across both, we may get situations like what's happening on the left. And there are other issues called edge effect. So what often happens is if we don't have complete data, then conclusions near the edge of your data has less confidence, and this should also be modeled. Whereas in the center, the confidence is higher, and I'm going to ignore that. So there are a few other issues that people talk about. Again, spatial statistics is a growing field. So some data sets, they have done quite a bit of theory development, like point data with point processes. But as you go to extended objects, graphs or spatio-temporal data, the theory is still evolving. And in case those issues become very important, I think we should involve spatial statisticians working on those areas and have collaboration. Okay, so let me pause here again and ask if there are any questions from more statistical or mathematical foundation. But basically the argument was that for spatial data, even the way statistics work or the techniques that we use, we need to sometimes go beyond classical statistics, at least go beyond i.i.d. assumption and try to avoid discretizing continuous space, because otherwise you face other kinds of problems.
So, Shashi, there's a question on the chat
Okay.
from Humayra. If you can talk a bit more on limitation of applying regression for spatial data.
Okay. So regression. So let's talk about the regression. Actually, I will come back and show that. So regression, remember, the i.i.d. assumption is black and white, right? I guess if you took statistics course, they've told you that. Now, spatial data violates i.i.d. assumption. So what happens? You can still fit regression to your data and it will give you something. But what gives, right? So number one thing, your goodness of fit, right? R square will be lower. If you accounted for i.i.d., and I will show you models who can do that, then you will get better R square. Okay, that's number one. Second, if you map your residual error, okay, if you map your residual error, remember your errors are supposed to be i.i.d. in ideal case. But since your model didn't capture that, you are going to see spatial patterns in your error. You may have a lot of positive error in one area and negative error in the other area and so on. So does that make sense? Of course, if you fit regression, it will give you something, but you are leaving a lot of opportunities on the table. It's a fine place to start, but you can do better. And I will actually show you better models in the next section when you are going to location prediction. So does that help, or do you want to paraphrase your question? Okay. All right. So we will come back to this regression question. It's a really good question to actually introduce the next section. But before I go there, I still want to ask, are there any questions on the statistical side at this point? Okay. So I will try to certainly build on things like regression, because many of us are very familiar with that. Okay. So let's talk about the regression, kind of problem. So here, this is the back to the spatial prediction. We are trying to predict where these nests are. And there are other spatial variables, which are explanatory variable. You can think of this data in a tabular fashion as well. There are about 5,000 pixels. So there is a grid on that. And so you can make a table with 5,000 rows, one per pixel. And there are about 7 columns here. One column will be this class variable called, is there a nest or not? And other columns would be these other explanatory variables, right? So you can make a table. And in fact, when this PhD student in ecology started, they first tried regression and neural network to predict the nest out of these, okay? And I will show you the result. But before that, let me mention about the spatial model that are used here. They use this neighbor graph that we were talking about it. They view it as a matrix. So if you had like the 4 locations, in this case, neighborhood is being defined by adjacency. So if I look at A, its only neighbor is B. So that's why you have 1 in this Boolean matrix. But B, everything else is neighbor. So you see 3 different ones and so on. So this is your basic Boolean neighborhood matrix. And this is row normalized. And this is done to improve some of the numerical and scientific algorithms, right? So So let me introduce some of these models. So here is your linear regression model, right? So you could say nest at a location, right? Its probability is basically defined by explanatory variable at that location, and we learn this weight beta. Okay, so this is your classical regression. Now in this world, if you just want to model autocorrelation, here is a model called spatial auto-regression model. And what it says is that nest at a location is only partially explained by explanatory variable at that location, but it is partially also explained by the nests in the neighborhood. So W is that neighborhood matrix, and these are the neighboring location nests. And this rho is a scalar, which is the degree of spatial autocorrelation. Okay, so this is called a spatial autoregression model. Some of us may have used it. But in this model, remember, this is a strict generalization because you can fit the data and rho will come out to be 0 if the nearby locations are independent, and you get back your linear regression. Okay, so this is a model where we are trying to model a little bit of spatial context. And this can be done in other models as well. If you know Bayesian classifier, it is trying to do it there. Decision tree, it's doing it there. Neural network world has also figured it out. And if you think about convolutional neural network, that's exactly what they are doing. The nearby pixels are looked at in classifying a particular pixel, right? So, but this is, this statistically, this is a very clean thing to talk about. In machine learning, they sometimes do it through regularizer, okay, which is a shortcut to improve computational speed, but there are trade-offs. But in any case, all it is saying is that try to make, don't assume nearby things are independent, okay? And here is sort of the difference from that PhD thesis. If when they did the classical regression, this is the ROC curve. And by using spatial autoregression, your prediction improved about 10 to 15% in this case, right? So this kind of giving you that if your phenomena exhibits or spatial autocorrelation, then this kind of models can help you. And even in classical world, if you think about, CNN is beating neural networks for many tasks in image recognition because they're the nearby things, there is a smoothness, right? So you see this kind of a thing. And this is exactly sort of the question that came up. Well, I can still try to push the linear regression through that and I will get something. So what gives? And this is what you lose. Your prediction accuracy is lower as shown here, and your residual error shows spatial patterns, right? So it was a perfect question to introduce this topic. Okay. All right, and those who are statistically more inclined, coming from machine learning, they may ask, well, why, should I do that? Because actually this is much more expensive to estimate. The least square is no longer an unbiased estimator for rho and beta if you go to spatial autoregression. And you have to use a slightly different estimation algorithm, which is computationally more expensive, which machine learning people often hate. And they take a shortcut by using the regularizer because now they can go back to least squares. So what do they give? And they basically, what they lose is, this bias. Their estimates are not going to be unbiased. And that's often problematic when you're doing out of sample generalization. So I'll spare the math because most people may not be interested in it. But let's talk about the second I, right? So I first talked about data samples are drawn independently of each other. And that's a, first law of geography says not a good idea. And many people have tried to get around it. And there are many techniques which are widely available now. But the second I, the work is a little bit less. And so let's talk about that, okay, for a minute. And in geographic or spatial world, we talk about spatial variability or spatial heterogeneity, right? So first, I'm giving you a very informal, intuitive reason why those things should be thought about. So even if you're coming from machine learning and so on, and you think your CNN and other classifiers, SVMs are great, you need to realize that there are situations without having the knowledge of location, it's very hard to separate things. So here I'm showing you a salt marsh, and here I'm showing you snow. And you can tell even as a human, it's not that easy to separate these, right? Probably if you had thermal signature and so on, you could probably separate them more easily. But in the visual band, they are very similar, right? But if you knew the location, right, in Gujarat, India, you are not going to see snow, right? So there's clearly not snow, and so on. So then if you knew the geographic location, your classification problem gets much easier, right? And this is something anybody who has done a large scale problem realizes that they run separate classifier for separate locations, okay? And here is another one, like global agricultural monitoring. Midwest, these are the farms, very large homogeneous farms, very, very easy to classify this. You can get away with very, coarse satellite imagery and simple classifiers. Here are the farms in China and India, okay? Very heterogeneous. So you can imagine the same sensor and same algorithm that works in Midwest may not work very well over here. And so if you do the global agricultural monitoring, there are 30 countries, they have different satellites, different instrumentation, different machine learning algorithm, right? So many people who deal with agriculture and climate and so on, they understand it intuitively, but many people in mathematics and machine learning feel that one size fit all and a single model should work everywhere. So anyway, there are people who are thinking about it. In the regression world, one of the well-known model is called geographically weighted regression, and it's implemented in ESRI and so on. And what they do is to say, well, I will leave the functional form alone, but these coefficients, the beta, individual coefficients are no longer scalars, but they are maps. Their values differ from place to place. Beta 1 is a map, beta 2 is a map. In other words, even though you're fitting regression model, but it's not single one size fit all, but your relative weights are being adjusted from place to place, okay? And I can have a quick show of hand. Has anyone used GWR, or are you familiar with GWR, just for curiosity? Tree is saying yes. Okay, great, wonderful. Now these ideas, as you can imagine, can probably can be taken further. So in the world of neural networks, right now still most of neural network is one size fit all world. But some work has started. So one of the thesis in my group is trying to generalize neural networks like CNN and so on to make them a little bit more flexible. So this is the classical neural network. Each weight is a scalar. And you can imagine a generalization of that where each weight is a map, right? And this is what we call spatial variability aware neural networks. And initial work actually shows if you do that, even if you separate a few locations, your classification accuracy improves to detect objects like urban garden and so on. But very early work in here. The idea of GWR taking it to other models can also pay off. So that's basically the message here. All right. Again, this area, there are a lot of other open problems, which are, still working, people are working on. One of which is sort of, how we evaluate our error functions itself. So let me actually give you 30 seconds to answer one other question. So suppose, that nest problem, here are the actual nests. And suppose we gridded this map. So these cells are saying A is actual nest. Now let's look at two models. First model predicts nests over here. So these are the prediction. This is a second model which predicts nest over there. And let me quickly ask you, which prediction do you prefer? So you can again put it in chat or just say verbally. Between prediction 1 and prediction 2, do you have a preference? Okay, so I see one person favoring prediction 2. Okay. Also prediction 2, prediction 2. Okay, great. So most of us are spatially oriented and we prefer that. By the way, if you ask, if you use that regular error function, precision, recall, or whatever else, total square error, they are identical. They both have 6 errors, right? So whether it's machine learning or statistics, they don't care. Whether C and D are same for them. But most of us are preferring the other one. So even how you model error and so on, there are things that can be improved, right? Okay. All right. So I'll pause here, see if there are any quick questions on the prediction models before we go to other methods and give you some highlights from there. All right, so let's go look at some other pattern families. As I said, location prediction is probably the more mature of things, and techniques have been developed and they're becoming available. So now let's think about detection of dense areas, the hotspot detection. And one of the popular algorithm is called dbScan. Some of us from maybe familiar with this, came from database world. And notice what happens when you subject it to some noise. So here is pure noise data, and notice dbScan is still finding the hotspots. Here is some test hotspot with some background noise, and see dbScan is getting fooled. Really what you wanted was this result. In other words, our clustering methods, if you many of them looking for dense areas, they are not thinking about background noise and so on. This is some very simple statistical test can do things which are a little bit better. So this is sort of a disconnect between some of our expectations. Now, first method that at least I am aware of, which started to check for statistical significance and try to reduce background noise, is SaTScan from National Cancer Institute, because they often get these complaints about, you have multiple cancer cases in this area. And first thing they try to check is whether that could have happened by chance. If that's the case, then they may not have to do further investigation. But if it passes this test, then they start doing more environmental investigation. So this is a very simple method. What it does is to look for circular regions, because computationally they are fairly simple. But for each circle that they generate, and even their circle generation is very simple. If you give them n points, they only look at n choose 2 circles. So every pair of point, one is at center, one is at perimeter. And for those circles, they first check the likelihood ratio, the inside density versus outside density. If that passes a threshold, then they check for statistical significance by basically generating a bunch of Monte Carlo simulations to generate complete spatial random and see how likely we are to get similar likelihood ratio, right? If it passes both thresholds, then they will say, okay, at least this particular dense area is statistically significant, and further investigation can happen from public health perspective. Now, as I showed you, if you run it on John Snow's data, certainly John Snow did it intuitively, but even SaTScan will say, yeah, this is an interesting cluster to look at. Here we are showing you another very simple example, Legionnaire disease in New York. And if you run it by this, it will find these dense areas it can pick up very easily. And then follow-up analysis can say, well, maybe the water tower, open opera house is close to many clusters, and we should test that and so on. So this is the first one. And then people have tried to find the balance, because dbScan can find arbitrary shape hotspot, whereas SaTScan only finds circular. So question is, how can you make SaTScan a little bit more flexible? So first, attempt happened more in the linear space, and I should first thank Vandana. Actually, she was the first one to look at hotspots on a road network, and her interest measures and so on were slightly different. They did not have a statistical part, but she actually articulated that this pattern is of interest, and we saw police department and others also express interest in these kind of patterns. Now, if you have, for example, road accidents and so on a linear space, if you run SaTScan, you notice that circles don't do a great job, because as soon as you try to put circle, there is a lot of empty area. So people try to generalize these circular hotspots to linear kind of hotspots, and others try to generalize it to ring shape and so on. But ultimately, you have to bite the bullet and say, can we work with more flexible shape? So another recent work, a couple of years ago, this was completed, and Ikun Zai is now with University of Maryland College Park. And what he did was to take dbScan metric and essentially add statistical significance, and then you can get these kind of desired things then. So this is just showing you that in hotspot detection, again, there are some unique angles which are of interest to spatial world, because the cost of false positive is often very high in many spatial applications. If you declare a neighborhood to be a hotspot of some disease, by mistake, the cost is very high, that this neighborhood gets stigmatized, people stop going, they lose business, politicians lose elections. So you have to be a little more careful than the average data mining applications. So that's mostly what I wanted to say about hotspots. Again, pause here, see if there are any quick questions in this case. Right?
I have a quick question. Can you go back to the? I'm not sure what's the significance in this figure. What's the difference between these two? What's the test means in the second row there?
Okay, that's a good question. So dbScan, you have to go back and look at what are the numeric metrics they are using, And for those numeric metrics, you can try to see, okay, suppose, I look at this particular color, right? I mean, one of these. And maybe it is the size of the cluster, right? And then you are asking that, with that neighborhood, can I get this size cluster in a complete spatial random? If I do 100 or 1,000 Monte Carlo simulation, how often can I get the kind of metric that dbScan got from this current data? Does that make sense? And if you can get that quite often in a complete spatial random, then you will say, well, even though DBScan caught it, it's not statistically significant, let's throw it out. And that's why it doesn't show up here. Whereas in the bottom case, when you see this T, it's right, much more dense and much number of points is much higher. If you try to do 1000 Monte Carlo simulation, the chances of this happening in a complete spatial random, as you can imagine, is extremely low. So this T survives the test, right? E survives the test, whereas these little things, they don't survive the test. Does that help at all?
Yeah, so now I can see that's the test is the one we want to recognize. So the significance is the significance of the noise?
Yeah, so your whatever cluster was detected by DBScan, we are trying to see that can that type of cluster show up in a complete spatial random.
Oh, okay. Spatial significance. Okay, thank you.
Yeah, statistical significance.
Okay, thank you. Yeah, got it.
Great. All right. So let's go to a little bit more on spatial outliers and then collocation. So spatial outliers is something, which is a little bit different than global outliers. And global outliers has been studied a lot in statistics as well as data mining. Spatial outliers are points which are very different from its neighbors. In data mining literature, some people think of local outliers, which are somewhat overlapping concept. But in spatial world, as I said, here this one observation, which is very different from its neighbors, and those are of interest here, right? And there are many tests which have been developed. So variogram cloud has been around in spatial world for a while. Here, what people do is to form pairs. So if you have n points here, you look at n choose 2 pairs, and you plot it in distance between the pairs and the difference between the attribute value, right? So if you do that, things which show up very high. So these are very high derivative points, and those pairs are then post-processed to find which point. So here S is showing up in both pairs, and it's very likely S is the spatial outlier. And once you take out S and from the data, and you can do it again, and you will notice that P and Q may not show up in any other pair. So these are some manual techniques. You can also develop an algorithmic technique, which is very simple. And here what is being done is that you're basically looking at a derivative. So each point, you compare the attribute value with the neighborhood average attribute value, and then you look at a distribution of that difference, right? So these are the points where the difference with their neighbors is very high. In this case, actually, the data, if data is normally distributed and your neighborhood size is fixed, you can actually use normal distribution type of tests, mu plus minus 3 sigma, to do this. So there are tests of this kind, primarily looking at the local derivatives, and people have used that, and this has been done for some spatio-temporal world as well. So here, this was on a water flow where you have different sensors looking at water quality. And again, they are basically accounting for the travel time because water flows at a certain speed. So you compare the attribute value at different location, accounting for the travel time. So in this particular project, it was one of the iHARP. We found that between these 2 points, the water quality was suddenly changing, which could not be explained by the speed. So you kind of say dissolved oxygen downstream was much higher than upstream, not fully explained by travel time. So further investigation basically showed that this was happening after a rainfall, and people felt that this pond's stagnant water was getting flushed through some underground channel to do that. But these are mostly discontinuity detection kind of tests, and the people do that. I'm going to skip the algorithmic part. One of the challenge here is the dependence between things. So if you're doing multiple outlier detection, algorithmically, it's a little bit harder. You have to do the highest one, remove it, and do it again. So there are some computational kinds of angles that are addressed here. So let me go for the last pattern family, collocation, and then we'll try to close. So this came, as a variation of what are called association rules in data mining, which was very, very popular around turn of century. It started by Walmart finding this pattern of diaper and beer in customer transactions. So here what is given is a set of things that each customer buys, and they are looking for pairs or triples of things which occur together in many transactions. Now, it turned out this data set was so big that they could not run correlation coefficient or chi-square. So they had come up with a slightly weaker statistics, which had much better computational property. Of course, there was a debate between statisticians and data miners about whether this, is statistically meaningful or not, but it took hold, right? This was very popular. Now, trying it on spatial data was also problematic because they needed transactions. So if I go back to the, which colors interact together, in order to run data mining, you have to transactionize this space. And this is exactly what Jaiwe Han did in his spatial association rule, without realizing that his results were sensitive to the partition, which I am showing you here. If you partition a space like this, these are 4 transactions, and the pattern you get is this, happening together. But if you transactionize differently, your pattern is this, and you do that, this happens. So Morimoto in 2004, acknowledged that, and this is where some of the people started looking at a graph model. So instead of going to transaction, our group and others used a neighbor graph approach that is common in spatial statistics. And what they essentially added to Ripley's cross-K function were some computational properties. They brought in this property which allows you to prune the search space quickly. And they did not give up completely on the statistics. They made sure their interest measure was related to what was known in spatial statistics. And it is actually showing you that. This is the new interest measure, and you notice that it's an upper bound. So spatial statisticians can also interpret whatever is coming out, right? And these kinds of models, actually, we have a current NSF grant where this is being used to develop and refine a physical model. So here you notice the original physical model. It has a lot of these errors. And what was done here is to look at which physical variables co-occur with these errors. And when that happens, you can essentially refine your model by partitioning it into parts or introducing new terms. And you kind of see how this model is improved by understanding what co-occurs with the high error situation, right? So just showing you that even in physical science, this can be done. Trends, there are many different ones, the algorithmic refinement. Also, the original collocation pattern did not have statistical significance added to it. And some people have added it for, for this one. And new work is also to think about adding time and so on. So for example, here, it is showing you that if you have certain event, at one time, little later in neighborhood, something else happens, and little later, something else happens. You can talk about cascade patterns like this, which can generate hypothesis for causation. And I think looking at the time, let me maybe go to the last slide and pause here. Basically, these are classical data mining things, and I argued that at many levels, you have to think a bit differently for spatial data. And going forth, I think spatio-temporal or looking at the terrain, and there are a lot of other open things. And hopefully we can think of new pattern families and work together. So with this, let me stop here and open for questions if there are some today. Okay. And as I said, the other slides give that details. We can look at those.
I have a quick question. I think one trend in the data mining community is recently is a graphic GAN graph neural network getting more and more popular. Do you think that's you mentioned the graph is a way to model the spatial relationship, right? I think do you think that's have a better like performance than CNN based on in terms of spatial applications?
Okay, so that's a very good question. So again, remember, what are the challenges, right? So one challenge was spatial autocorrelation, in which case you want to be aware of your neighbors, right? And graph can help you there. So for example, CNN kind of does that, and you can go to graph CNN. So your autocorrelation modeling may be pretty, graphs can help. But another challenge was spatial variability or heterogeneity, right? And you can ask yourself in graph CNN, do they again do one size fit all, or do they allow the network weights to vary from place to place, right? Have you seen any such work in graph CNN?
No, I'm just
right.
hear your opinion on GN.
Right. So all I'm saying is, it's good. The autocorrelation part, just like CNN, it can do better. Transformer and CNN are already showing that accounting for neighbors or long distance relationship can help, and graphs can help that. But heterogeneity variability, I think one would have to extend it. Another one, which I will really ask a far out question, is statistical significance. Do you think noise can fool your graph CNN?
Maybe, I think.
Right, in face detection in CNN, people have shown that you just add a few pixels in a stop sign and suddenly it looks like something else, right? So whole neural network literature hasn't thought about noise, right? I mean, of course, computationally it will be very expensive, but that should be music to the ears of computer scientists, right? And so all I'm saying is, yeah, graph can help to model the neighbor relationship, but that's one of the challenges, and there are other challenges that we should think about, right?
Couple of things on the chat. I think folks are asking for the reference materials to be posted on Slack. So the last couple of slides.
Okay.
And then another question from Atefa about the Pearson correlation. Does that not work well on all spatial data?
Okay. So the survey, I will be glad. I think that the starting point, just these couple of these would be pretty good places to start. And I will be glad to share that on Slack with help of Vandana, because I'm not as active there. Sure. But let's think about Pearson correlation coefficient. And I was saying it doesn't work well on all spatial data. The catch here is that, as far as I know, Pearson correlation coefficient is based on vector algebra, right? So if you have a continuous data like a map, then the only way I know how to use it is to somehow discretize that space. And as soon as you discretize it, your results are sensitive to the way you partition it. So that was the reason I was kind of saying that you have to be careful and at least disclose what partition you're using. So it is possible that in some cases, the partitions are consensus partition, like census data, right? There is a one standard way to partition it and everybody uses that. And maybe in that world, you can say, look, I'm just using census partitioning, but disclose it. Are you using census block or block group or tract, or what are you using? Because even those choices will change your value, right? So it's conceivable that you are in a space where there is a consensus partitioning like zip code or something, and everybody uses that, and your Pearson correlation coefficient is conditioned on that. But if there is more than one way to partition, then you have to disclose the sensitivity. That's the way I would put it. I don't know if that helps or if that's what you were looking for. Key thing is disclosure, because your results will not be unique,
I think Tree has another question. Go ahead, Tree.
Go ahead.
It's very specific, but going back to the CNNs can be fooled by noise.
Yes.
Has this ever been, I guess I'm assuming this has been done about clouds in particular in large scale imagery. Do you know of any examples of that, or?
Clouds, I do not know, but I can show you a lot of, in fact, it was in, very popular magazine like Popular Science. They were showing that for traffic science and so on, you throw a little bit of noise and CNN will suddenly give you very wrong outputs. And I will be glad to share those articles. But your very interesting question, you're saying what happens if you put in cloud there, right?
It's pretty much the first thing I think of is that the CNN, the very bad CNN that I've created before, for example, or everything gets fooled by clouds. And I think this is a very common problem all across, not just in polar science, but everywhere. You also have a problem where you notice that salt fields looked like snow. Well, snow looks like clouds.
Yeah.
So I'm more attaching a problem in your discipline to something that I think is a very real thing in polar science.
Yes. No,
That's
I think
all I have
that will
to
be
say.
very cool. Do you?
Yeah.
We could try it. Are there any models of cloud? I mean, have people tried to generate synthetic cloud, or there? Because one could try to study what happens to CNN's behavior if you have different type of cloud.
Yeah, I think honestly, just throwing with visible imagery. So usually with at microwave ranges and stuff, it sees through clouds, and that's what often gets used. But some of the most frequent imagery that we have isn't able to distinguish clouds very well, and so there's a lot of models in this that they used for it. But it just occurs to me that you can use to be able to figure out that the noise, and this is very intuitive. Sorry if it's a little silly, but that you could know it's a cloud because you've seen a picture of the same thing a couple days ago and it looked similar. So when we've talked about lakes, for example, but I think it's with a lot of things. So I guess I'm just seeing this as a place where, if this is a problem in computer science, I'm linking it directly to a problem of clouds in visual imagery over places that have lots of snow. Like,
yeah, no, this will be cool. And as at some cases, visually cloud and snow also may have overlap, right? Yeah.
oh yeah, completely. And it confuses everything.
Yeah, no, that would be a very cool one. I think we should discuss it a little bit more.
Yeah, sure.
That will be good. Yeah.
Okay.
And
Great.
is this something even because, your case, you have many other bands beyond visual, right? You have thermal and others.
Well, it depends. That's why I bring up the specific case that I'm thinking of is planet imagery, which is just visible imagery. And so you have these nice, cheap little iPhones thrown into space that give you a lot of imagery, but it can't see through clouds very well.
Right.
And even with a lot of other imagery, it's pretty difficult because low clouds act differently than and resolving. I mean, I'm not sure, so I can sort of
No, this
revisit.
will be very cool because as Jianwu and others will say, in CNN world, thinking about noise, I mean, people have shown it fools CNN, but they haven't figured out ways around it, apart from maybe GAN, is maybe one technique where people have tried to fight noise and other adversarial things. But yeah, it will be very cool. Maybe a GAN for cloud, I don't know.
Well, I can throw another one in there, which is the cloud also gets confused with things like ice layers on a lake. So there's just a lot of these kind of intuitively a mess where the shape of it might be able to give you information, whatever. But we can discuss this at a later date. It's just a problem that I thought of in the context of this.
Certainly thought-provoking.
Cool.
That's great. Looking at the time, maybe one last question, if anybody has any question. I'm sure Shashi, you'll have lots of follow-up as well. I'm just going to give it a pause for a second. So I'm sure, Shashi, there'll be follow-up. If you can send me the references, I can put it on Slack and share with folks.
Sure.
But thank you so much for this talk. It was very comprehensive. And thank you so much.
Thank you, everyone. Really appreciate cool questions and your attention.